Hello everyone, my name is Hugo Blan, and I'm currently working at PSL University in Paris within the Cauer laboratory at Mainz Paris School. Today I am excited to present to you our research paper entitled RayGauss, Volumetric Gaussian-Based Raycasting for Photorealistic Novel View Synthesis. Our approach aims to approximate the radiance and density fields of a scene using raycasting of irregularly distributed kernels. This enables us to generate photorealistic novel views of the scene and visualize them interactively. The first question you might ask if you're not familiar with the field is, what exactly is photorealistic novel view synthesis? In simple terms, imagine you have a set of photographs of a scene, along with the positions from which these photos were taken. The goal of novel view synthesis is to generate new images of the scene as it would appear from viewpoints that were not originally captured. This field has seen significant advancements in recent years, particularly with the publication of the paper NERF, representing scenes as neural radiance fields for view synthesis. One of the key contributions of this paper is the use of a discretized volumetric rendering equation to optimize the parameters of a scene. Here's how it works. NERF employs an equation from the field of volumetric rendering. This equation describes the interaction of light with an emissive and absorbing medium. In such a medium, the interaction of light can be modeled by the following radiative transfer equation. This equation has an exact solution that allows us to express the radiance perceived at a given point from a specific direction as follows. This means we can calculate the radiance received by a sensor by integrating the properties of the medium along a ray. Since this formulation involves an integral, numerical computation requires an approximated, discretized version of the equation to make it practical. This numerical model is traditionally used to render scenes with known volumetric properties. What makes NERF's approach innovative is that it uses this equation to retrieve the scene's parameters by leveraging rendered images of the scene. To achieve this, they introduce a parametric representation of the scene using a neural network which encodes the radiance and density fields at every point within the scene. The weights of this neural network are optimized such that the rendered images from known viewpoints computed using the volumetric rendering equation and the neural network match the actual images of the scene. NERF has enabled the generation of new photorealistic views from photographs of real-world scenes. However, despite the high-quality results achieved by this method, a significant challenge remains: its reliance on a computationally expensive neural network to compute the radiance and density fields for each sample. This reliance makes both the optimization and inference processes relatively slow, highlighting the need for further improvements to enhance performance and efficiency. Additionally, numerous subsequent research efforts have improved the representation of radiance and density fields. Their objective has been to develop data structures that better adapt to the scene's geometry while locally storing the parameters that define local appearance. This allows the appearance to be described using a small set of local parameters, which are more capable of finely adapting to the appearance and geometry without requiring evaluation of an entire neural network. Various works have followed this direction and have succeeded in accelerating computation times and improving rendering quality. Notable examples include works such as Planoxel's DirectVoxGo, TetraNERF, and Instant NGP, which use voxel grids, sets of tetrahedra, and hash grids to store the parameters. However, these approaches remain limited by the resolution of the underlying structure. Other competing approaches have leveraged irregularly distributed points in space to represent the scene. Noteworthy examples include Point NERF, which delivers great graphical results, and 3D Gaussian splatting, which achieves faster computation times while maintaining high-quality outputs. However, the first approach is limited in speed due to its reliance on neural networks and further constrained by the use of a relatively small number of points to compute the density and radiance fields. Meanwhile, the second approach relies on a splatting algorithm which inherently produces rendering artifacts such as flickering. Our work is inspired by this branch of research and focuses specifically on point cloud-inspired representations. Our objective is to develop a differentiable volume ray casting algorithm capable of rendering primitives represented by elliptical basis functions. By using an optimization process similar to NERF, we aim to learn the volumetric representation of a real-world scene and generate new views. The interest in this approach is twofold. Elliptical basis functions can efficiently adapt to the geometry of the scene, and raycasting of these primitives, provided sufficient sampling, promises to produce minimal artifacts. However, we need to find a consistent way to introduce this type of primitive and implement an efficient rendering method capable of enabling the fast rendering of such primitives. From a physical perspective, each primitive in our scene will represent an independent entity emitting and absorbing light. From a mathematical perspective, the radiance and density fields can be described as a weighted linear combination of basis functions. To derive this mathematical expression for the radiance and density fields, we assume that the individual density of a primitive can be described as the product of a decreasing elliptical basis function and a scalar. As a result, the density will be highest at the center of the primitive and will decrease radially as the distance from the primitive increases. Additionally, the radiance emitted by this primitive will depend solely on the observation direction and will be parameterized by a combination of spherical harmonics and spherical Gaussians. From these individual fields associated with each primitive, we can derive a global density and emitted radiance field representing the entire scene. This can be illustrated by reintroducing the radiative transfer equation. In the case of a medium containing n independent entities, this equation takes the following form. Thus, we can deduce the global density and radiance fields representing our scene. To obtain the final form of our fields, we simply need to specify the shape of the elliptical basis function used. Empirically, an anisotropic Gaussian function has been shown to yield good results, so we adopt this function to derive the final form of our density and emitted radiance fields. This formulation ensures physical consistency while introducing the use of elliptical basis functions for our sparsely distributed primitives. Now that we have the representation of our scene, we need to achieve an efficient differentiable rendering of it. To achieve this, we decide to leverage an acceleration structure that allows for efficiently computing the intersection between a given ray and the primitives of our scene. A bounding volume hierarchy, BVH, is a strong candidate as it has optimized implementations available through APIs such as optics. However, to use this structure, we need spatially bounded primitives, which is not the case with our anisotropic Gaussian functions, as they have an unbounded support. To address this challenge, we take advantage of the fact that the Gaussian function quickly becomes negligible as one moves away from its mean. Thus, to bound the primitives, we decide to restrict their evaluation to the region where their density exceeds a given threshold. This approach allows us to compute the axis-aligned bounding boxes required for constructing the BVH and reduces the evaluation cost of our global radiance and density fields. With this approach, we can now construct the BVH to accelerate ray primitive intersection computations. To do this, we start by calculating the bounding boxes enclosing our primitives, and then use a dedicated API to build the BVH. To efficiently leverage the BVH structure and reduce the number of intersection computations, we adopt the following approach. For each ray, we traverse the scene by evaluating the discretized rendering equation over successive segments, each containing multiple samples. This allows us to compute the intersections of multiple samples with our primitives directly, thereby reducing the computational cost of intersection calculations. The complete rendering process is detailed in the figure shown nearby. Thus, it becomes possible to render our primitives through ray casting. Additionally, we can employ a process similar to that of NeRF to optimize the parameters of these primitives, enabling them to accurately represent our scene. The various modeling choices are validated through empirical tests, which demonstrate that anisotropic Gaussians combined with spherical harmonics and spherical Gaussians achieve the most accurate rendering through volume ray casting. Thus, this approach enables us to achieve excellent graphical results, rivaling the best current method, while maintaining reasonable training and inference times, thanks to our efficient implementation. More concretely, this approach allows for high-quality rendering of scenes captured with just a few photos, such as this archaeological artifact, the Coupe d'Autun from the Rollin Museum, discovered in 2020 in the Christian necropolis of Saint-Pierre-l'Estrier, dating back to the 4th century AD.